Also, as a woman, I live right by a train. So if a train rolls by, I'm going to mute myself for 10 seconds, just so everybody knows. Or I'll leave myself unmuted so you know I'm not faking it. But there might be a train that goes by. Okay, I think that's everybody. All right, so morning, everybody. Sorry for the late notice, but I'm not gonna be a super spreader. So if I'm fine, but sore throat, I'm staying home. So hopefully everybody had a good weekend. Today, there we go. Today we're going to be talking about the first derivative test and increasing and decreasing functions. These are both really important ideas if you ever want to get a really good sketch of a graph that you're of a function that you're looking at. If you want to sketch it somewhat accurately, you'll need what we learned this week, though I'm probably never going to test you on curve sketching. But just so you know, traditionally that's what the lessons that we're learning this week, that's what that has been applied to, is curve sketching. Okay. So some announcements. You have homework due tonight at 11:59 p.m. If you have any questions on it, I'm holding office hours online today, obviously, so you can just use this same Zoom room that you're in to drop in on my office hours. Okay. There's also homework for week 8 has been assigned in Canvas. It is over the first and second derivative test and increasing and decreasing functions and concavity. Okay, so that should be visible in Canvas now. I'll post the answer key for last week's homework after class. There were a few late submissions, but I'll post the answer key after class. So then also last announcement is that exam 2 is Friday of next week. What we learned today is going to be on there. So it's covering everything from the last exam, exam 1, up until the end of this week. Okay, so everything this week is fair game on the exam. And that's October 23rd. Okay. Any questions? Okay, well, let's get started then. So last time we learned about last week we learned about several important theorems, including the extreme value theorem. I guess was that 2 weeks ago? We learned the extreme value theorem, which lets us find the absolute maxima and minima of a function on a closed interval. We learned about Rolle's theorem and the mean value theorem. Rolle's theorem is actually a special case of the mean value theorem, and the mean value theorem simply says if you have a function that is on a closed interval, a to b, you have a function that's continuous on some closed interval and differentiable on the open interval, then you can find a tangent line that is parallel to the secant line, right? That's what the mean value theorem says. And Rolle's theorem is just a special case where f of a is equal to f of b. Okay. Mean value theorem is very important. I'm going to be using all the proofs today that I do are relying on the mean value theorem. Okay, so the extreme value theorem guaranteed that if we are looking at a continuous function on a closed interval, that it has an absolute maximum and an absolute minimum value on that interval, which isn't guaranteed on an open interval, right? We saw of cases where if we were looking at a continuous function on an open interval, there's no guarantee that there's a maximum or a minimum value. Similarly, if the function is not continuous, there's also no guarantee of a maximum or minimum value. So that is not a trivial thing. Okay, but this week we're going to learn about how we can determine when the relative extrema inside of an interval, or if we're not even looking at a closed interval, but we find relative maxima and minima, we can determine when those are actually relative maxes or relative mins from a few pretty easy tests. So today we're going to learn, if I have time, we're going to learn about the what's called the first derivative test, and then Thursday we're going to learn about the second derivative test. Okay, so these both help us determine if I'm looking at a function and I know critical points. So there's a critical number and there's a critical number, right? If I know these just from using calculus, taking the first derivative and setting it equal to 0, I can use the first derivative test to determine if this is a relative max or relative min, and from the graph it's a relative maximum, but we don't always have the graph. So this is going to tell us when something is a relative max or a relative min without looking at the graph at all, only looking at the first derivative, which is pretty useful. Okay? So first we need to know what it means for a function to be increasing or decreasing on an interval to be able to use the first derivative test. Okay? So a few definitions are in order. So a function is increasing. This function is f increasing. It doesn't have to be continuous or differentiable or anything. Okay, I'm not assuming anything about f for this definition. So a function f is increasing on an interval if f of x1 is less than f of x2 whenever x1 is less than x2 for each x1 and x2 in the interval. Okay, so if I draw a graph of an increasing function, here's x1, x2, and the function's increasing in some interval, okay? So, I mean, just a straight line is increasing, right? Because if I take x1, there's f of x1, and x2, there's f of x, okay? So, f of x2 is clearly greater than f of x1, and x1 or x2 is greater than x1, okay? So that clearly holds for every choice of x1 and x2 in this interval AB. So we would say f of x is increasing on this interval A to B. So a function f is decreasing on an interval if it's increasing when f of x1 is less than f of x2, when x1 is less than x2, then what do we think it means for it to be decreasing? Here comes a train, just so everybody knows. There we go. That wasn't so bad. So what does it mean for a function to be decreasing? When x1 is less than x2, then what would we expect to see from f of x1 and f of x2? I'm going to write f of x1, f of x2. What should I put between those two? What was that?
X1 is greater.
Yes, f of x1 is greater than f of x2. Perfect. F of x1 is greater than f of x2 whenever x1 is less than x2. Okay, so it's the exact opposite of this picture down here. So I'll draw a decreasing function now on this interval A to B. Oops. On this interval A to B. This function here that I'm drawing is decreasing, right? If I take any x1 and and any x2 in here? Well, here's f of x1, here's f of x2, and x2 is bigger than x1, but f of x2 is smaller than f of x1, right? So that means, and if you pick any 2 points in this interval a to b, that's going to hold. So this function is decreasing on the interval a to b. Okay. Some books will use the terminology increasing and decreasing to mean that instead of strict inequality, we have less than or equal to, or greater than or equal to here. Okay. Your book does not. So, but just so you know, some books do that. So we're going to stick with strict inequality. So there's a question in the chat. So this helps us without looking at the graph. Yes, that's exactly right. This will help us if we don't have the graph of the function. We just need to check this condition to see whether f of x is increasing or decreasing on an interval. And really, this condition, like I said, f of x doesn't need to be continuous or differentiable or anything. So really, this condition for a general function is not so easy to check. For differentiable functions, which is what we care about in calculus, there's going to be a condition that's much easier to check than just picking any 2 points and seeing whether f of x1 is bigger than or smaller than f of x2. Okay. So are there any questions about the definitions of increasing and decreasing? All right, so like I said, if we know a special thing about f of x, then specifically that is differentiable, then we have an easy way to check if the function is increasing or decreasing on an open interval. Okay, so a differentiable function, which this function is going to be called f. The function is f of x is increasing. So right now this is just for increasing on an open interval a to b if and only if f of x, or sorry, f prime of x is greater than 0. Yes, exactly. This just means the slope is positive for every x in the interval a to b. Okay. So there's 2 key things, 2 key conditions. One, f of x is differentiable, okay? Without differentiability, we don't have this easy check to see if f of x is increasing. And the second thing about this theorem, I say if and only if. In mathematics, this means that we need to prove this what's called both ways. I need to show that a differentiable function that's increasing satisfies f prime of x is greater than 0 for every x. I also need to show that if f prime of x is greater than 0 for every x in the interval, then f of x is increasing. Okay. So, a proof of this fact. So first I'm going to assume f prime of x is greater than 0 for x in the interval a to b. Okay, so I'm starting with f prime of x is greater than 0. Then I need to show that if x1 is less than x2, then f of x1 is less than f of x2, right? I'm assuming f prime is bigger than 0. I want to use that to show that f is increasing, which is exactly what I wrote for need to show. Okay, so how are we going to prove this? Well, I am going to take any x1 and x2 in the interval a to b. Okay, another way to show this fact, another way to show that x1 less than x2, then f of x1 is less than f of x2. Another way to say that is x1 less than x2, then f of x2 minus f of x1 is greater than 0. Right? Does everybody see that? If I subtract this from both sides of that equality, then I would end up with this. So I'm going to try to show this, okay? That's what I'm going to try to show. And the way I'm going to do that is with the all-important, all-powerful mean value theorem, okay? So x1, and x2 are in the interval a to b, okay? And that's where f prime of x exists. So that means, so f is continuous on the smaller interval, x1 to x2, on the smaller closed interval x1 to x2, right? Because if I draw the number line, I've got A and I've got B. This is the open interval, and then I'm picking x1 in here and x2 somewhere else to the right of x1. So because f is differentiable on the whole interval a to b, f is going to be differentiable and continuous on the interval x1 to x2. Okay. So f is continuous on the closed interval x1 to x2 and differentiable on the open interval x1 to x2. Okay, so I can apply the mean value theorem to f on the interval x1 to x2. So the mean value theorem says then, so there's a number c in the interval, in the open interval x1 to x2, such that, well, the mean value theorem says that that c satisfies f prime of c is equal to f of x2 minus f of x1 divided by x2 minus x1. Okay. But then what do we know about this? I'm assuming, what about f prime on the whole interval a to b? Yes, exactly. I'm assuming f prime of x is bigger than 0, right? So I know that, that this, which is equal to this, I know that this is bigger than 0, right? I chose x2 greater than x1, right? I mean, I wrote it as x1 is less than x2, but that's the same thing. So what can I say about x2 minus x1?
It's greater than 0.
Perfect. This is also greater than 0. So I have f of x2 minus f of x1 over x2 minus x1 is bigger than 0. And I know that this is bigger than 0. So what can I say about f of x2 minus f of x1? If I divide two numbers and I get a positive number, and I know the denominator is positive, then the top has to be what? Yes, the top also has to be positive. Thank you, Saba. It is bigger than 0. Does everybody see that? If I divide two numbers and the answer is positive and the denominator is positive, then the top has to be positive. Okay. So this is exactly what we wanted to show. This tells us that f of x is increasing. Wow, my handwriting could not have been worse there. Increasing on the open interval a to b, because I picked x1 and x2 to be any old numbers in the interval, so it has to hold on the whole interval. Okay. Questions on that? Is this proof? No, you don't need to know this proof for the exam. There are very few proofs that I'm gonna ever want you to be able to reproduce on an exam. There's one more part of this proof though, because we showed that if f prime is positive, that means f is increasing. But I also need to show that if f is increasing, then that means f prime is positive. And that is just going to rely on the fact that, or it's just going to rely on the definition of the derivative, okay? So now we're going to assume f is increasing. If f is increasing, then if x is in the interval, the open interval a to b, then we have f prime of x, which is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Well, this is really, h is really where that h comes from, is x plus h minus x, right? Well, let's say for a second h is positive. If h is bigger than 0, then the bottom is positive, right? And the top, well, if h is positive, then x plus h is bigger than x. So the top is also positive, because we're assuming now that f is increasing, and I want to show that f prime is bigger than 0. Okay. But then I'm taking the limit as h goes to 0 of a positive thing divided by a positive thing. And so that has to equal the limit as h approaches 0 of a positive thing divided by a positive thing, which is going to be positive. Okay. Now I'm being a little relaxed here. This is actually, I can only guarantee that this is greater than or equal to 0, which is why some books define increasing with greater than or equal to, or less than or equal to for decreasing. Um, that's why some books define that way. But we're just going to assume that that it's a strict inequality, which isn't technically correct, but it doesn't really matter. The real thing we wanted to show was the other direction, which we already showed. Okay. So, are there any questions? Okay. So, there's an almost identical result for a decreasing function on an open interval. Okay. So, a differentiable function is decreasing on an open interval. And again, the function here is f. Oops. A differentiable function is decreasing on an open interval a to b if and only if f prime of x is less than, strictly less than 0 for each x in the interval a to b. Okay, and the proof is almost identical, and I would encourage you guys to actually try it on your own. You essentially just need to change the direction of a few inequality signs, but it's good practice to try and prove this on your own. Okay. So lastly, with increasing and decreasing, we looked at these strict inequalities, and if f prime of x is equal to 0 on an interval a to b, then we showed last time that that means f is constant on the interval a to b. Okay, if f prime of x is equal to 0 for one point x, then that is a critical number. But if f prime of x is equal to 0 on a whole interval, then that means f of x is constant on that interval. Those are still all critical numbers, but it's just going to be a funny looking graph. Okay. So are there any questions before we move on to actually finding intervals on which a function is increasing or decreasing? Okay. So guidelines. We've got a few guidelines for finding intervals of increasing or decreasing for a function. Okay. So we're going to say f of x is a continuous function on the open interval a to b. Okay. So to find the open intervals on which f is increasing or decreasing, we're going to use the following steps. Okay, so step 1, locate the critical numbers. This is critical numbers of f in the interval a to b, and then we're going to use these to determine test intervals. And I'll show you what I mean by that in an example problem here in a second. Okay, but locating critical numbers is critical here. Okay. Step 2, we're going to determine the sign of f prime of x at one test value in each of the intervals we find from step 1. Step 3, we're going to use the sign of f prime to determine whether f is increasing, or, decreasing. On each interval. So I stated these guidelines for an open interval a to b, but this holds even if you're on infinitely big intervals. So minus infinity to b, or a to infinity, or even minus infinity to infinity. Okay. So these guidelines work on all of these open intervals. Okay. And critical numbers, by the way, in case anyone has forgotten, critical numbers are where either f prime of x equals 0, or this is one that people forget, f prime of x does not exist. Okay. All right, so example, we're going to find all the open intervals where the function f of x equals x times e to the x is increasing or decreasing. Okay. All right, so step one. What was step one?
Find critical numbers.
Exactly, we're going to find these critical numbers. So to do that, I'm going to find f prime of x. Well, this is the derivative of f with respect to x. F of x is x times e to the x. So how do I find that derivative?
Product rule.
Perfect. I need to use the product rule here. So the product rule says I'm going to take the derivative of the first function. The derivative of x with respect to x is just 1 times. Then I'll leave the second function alone, times e to the x. Plus, then I'll leave the first function alone, x, and then I'll take the derivative of e to the x. So what's the derivative? The derivative of e to the x.
E to the x.
Perfect, e to the x. And to help us out here, I'm going to write this as, I'm going to factor out each of these terms has an e to the x, right? So I'm going to factor out e to the x, and I'm left with e to the x times 1 plus x. And so what do I want to do with this? Yeah, exactly. I'm going to set that equal to 0. Okay. So I have this product of two things is equal to 0. So that means either e to the x is 0 or 1 plus x is 0. Is e to the x ever 0?
No.
No, it's never ever 0. Don't ever try to solve e to the x equals 0 because it's not ever 0. Okay. And then where does 1 plus x equal 0? Yes, exactly. X equals -1. Perfect. So then that gives me my test intervals. I notice that I say find all open intervals where the function f of x equals x times e to the x is increasing or decreasing. I didn't give you a starting interval a to b. So if I don't give you a starting interval, you assume that the starting interval is just the domain of the function. Okay? And the domain of this function, well, what numbers can I plug into that? I can plug in all of them, right? So the starting interval here is actually minus infinity to infinity. Okay. So I got an x value of x equals -1. So that tells me that my test intervals from step 1, use these to determine test intervals, are minus infinity to -1, and then -1 to positive infinity. Okay. So with these problems, I always make a table. Okay. So then on the left, I'm going to have just f prime of x is e to the x times 1 plus x. Okay. So we've determined our test intervals. Our test intervals are minus infinity to -1 and -1 to positive infinity. Okay. So then I need to determine what's happening inside each of these intervals, whether f prime of x is positive or negative inside each of these intervals. So let's pick a test point in the interval minus infinity to minus 1. Well, what's a number in that interval? Yeah, exactly. -2. Thank you in the chat. So -2 is in that interval, right? So what sign does f prime of -2 have? Well, e to the -2, is that positive or negative? Careful. Let's look at a graph of e to the x really quick. If I do e to the x, no matter how far I zoom out, it stays above the x-axis, right? E to the x is actually always positive. Okay, so this is always bigger than 0. This is always going to be positive. And so what sign does 1 plus -2? We're picking x equals -2 here to test. So what sign does 1 plus -2 have? Yeah, it's negative. So I'm going to get a positive times a negative is going to give me a negative on this interval, right? Okay. So again, here we checked -2. What value should we check in this interval? In the interval 1 to infinity? Yeah, 0, exactly. So what sign does e to the x have? Well, that's going to be positive, right? E to the 0 is 1, that's positive. And then what sign does 1 plus 0 have?
Still positive.
That's also positive, right? So I'm going to get a positive times a positive is going to give me a positive. Oops. Positive. So that means that f of x on this interval, I always like to, so this is f prime of x. I always like to draw what f of x roughly is doing underneath my table. So f of x on the interval -infinity to -1, well, f prime of x is negative there. So f of x has to be decreasing, right? And then in the interval -1 to infinity, f of x is increasing there because f prime of x is positive. So f of x is increasing. And so I'm jumping a little ahead here, but looking at what f of x is doing on these intervals, we have a critical number at x equals -1, right? So do we think at x equals -1, that's going to be a relative maximum or a relative minimum? Just looking at what f of x is going from decreasing to increasing. So is that going to be a relative max or relative min there, you think?
Minimum.
Mm-hmm. Exactly. This is a continuous function. It's going to have to bottom out, but we'll get to that. That is essentially, we just did the first derivative test, okay? But we do need to give a final answer here, okay? So my final answer, this table, honestly, the table, if you're in a time crunch and you just have this table on the exam, that's going to be fine for me. But you should write out your full answer. F is increasing on the interval, well, it's increasing here, right? On the interval -1 to positive infinity. -1 to positive infinity. Okay. And then f is decreasing on the interval -infinity to -1. Okay. This technically is your final answer for this problem. Again, if you're in a time crunch and you have this table written on an exam, that's going to get you all the points, but you should write out this as your full answer. Are there any questions on this? Let's look at another problem. Find the open intervals where f of x equals x to the third minus 3/2 x squared is increasing or decreasing. All right, so we're finding intervals of increasing and decreasing. So what should we do first?
Critical numbers.
Yes, exactly. Find the critical numbers. So I'm going to find f prime of x. Well, what's f prime? What's the derivative of x cubed with respect to x?
3x squared.
3x squared, perfect. And then what's the derivative of -3/2 times x squared with respect to x?
3x.
Perfect. So I'm going to do -3x. Perfect. I'm going to set this equal to 0. So the left-hand side here, I can factor, right? So I can, both of these guys have a 3x in common. So when I factor out 3x from this first term, I'm going to get, well, just an x, right? I'll be left with an x there. And then when I factor the 3x out from here, I'm just going to be left with a -1. Okay. So what are my critical numbers then?
Zero and 1.
Perfect. I get x equals 0 from this factor, setting this factor equal to 0, x equals 0. And when I set this factor equal to 0, I just get x equals 1. Okay. So then my test intervals, again, this function is defined for all real numbers. So my test intervals are going to be -infinity to 0, 0 to 1, and 1 to infinity. So the way this table is always going to go is you're going to list your a value and then all your critical numbers in order, and then your b value here. Okay. So these are my test intervals. All right. So one other thing I like to do when I'm making this table is if I have a product of things like this, I like to write out 3x, x minus 1, and then f prime of x is their product. All right, so let's take this one factor at a time. So first of all, what test point should I plug in between x equals, or between -infinity and 0? What test value should I plug in? Yes,
-1.
Yeah, -1 is a perfect choice. So what sign does 3x have when x is -1?
Negative.
Negative, good. What sign does x minus 1 have when x is -1?
Negative.
Negative. So f prime of x is their product, right? So I'm going to get a negative times a negative gives me a positive. Okay. Very good. What test value should I plug in between x equals 0 and x equals 1?
X equals 1/2.
Yeah, 1/2 is a perfect choice. Okay, so what sign does 3x have when x is 1/2?
Positive.
Positive, good. What sign does x minus 1 have when x is 1/2?
Negative.
Negative. And so f prime, what sign is that going to have?
Negative.
Negative. Good. It's a positive times a negative gives me a negative. Good. Lastly, what test number should I plug in between 1 and infinity?
X equals 2.
2. Very good. Well, I'm going to use x equals 2 here. So what sign does 3x have when x is 2?
Positive.
Positive. What sign does x minus 1 have when x is 2?
Positive.
Positive. So what sign does f prime have when x is 2?
Positive.
Positive. Very good. So if I sketch just a very rough sketch of what f is doing on these intervals from minus infinity to 0, f is increasing, right? F prime is positive there, so f is increasing. From 0 to 1, f of x is decreasing. And from 1 to infinity, f is increasing again, right? So again, the first derivative tests, we're going to learn that tomorrow now. But you can even just see, just from from the sketch, what has to be true is that we're going to have a max at x equals 0 and a min at x equals 1, right? But we're going to prove that tomorrow. So our final answer then for this problem, f is, I'll do decreasing first, decreasing on what interval?
0 to 1.
0 to 1, perfect. And then f is increasing on, well, it's increasing on minus infinity to 0, right? And what other interval?
1 to
1 plus
infinity.
infinity.
Perfect. 1 to infinity. Okay. And so the way we say it's increasing on both of these is I write both of those intervals down and I put a big U between them. Okay. This is math speak for f is increasing on both of these intervals. The U, the big U, stands for union, which again just means take both of these intervals. Are there any questions about this? This is your final answer. Okay. If you want to just write f is increasing on minus infinity to 0 and 1 to infinity, that would be fine too. For anyone who wants to be a math major, which should be all of you, you should get used to writing this U because that's going to come up in your math career quite a bit. So, any questions? All right. So I don't have any time to do this next problem, but so we'll pick up from here tomorrow, and we'll do this example tomorrow, and then we'll formally learn the first derivative test. Okay. So if we don't have any questions, you can feel free to head out. If you do have any questions, you can stick around and ask. Also, remember I have office hours today. You can use the same Zoom room to log on. Okay. So thank you all for being here.
Thank you.
Thank you.